Welcome to the NeurIPS Weather Forecast 2022 competition track session. So it's my job here today to first give a brief introduction before the more interesting talks start, presenting the highlights of this year's competition. The Weather Forecast 2022 challenge was taking a step to go beyond what we've done last year in the first Weather Forecast episode. This year, a key challenge was to actually predict weather in super resolution and under spatial-temporal shifts. The challenge included the step to go from low resolution and highly abundant satellite images to high resolution rain. It involved a transfer learning challenge where models had to be trained on data in some areas and at some time, and then had to predict rain actually in a different location in Europe and at a different time. And the distributional shifts across these different regions and times could actually be quite strong. Last but not least, the input consisted of multiple bands of satellite image sensors. So people actually had the opportunity to fuse information across these different channels and also incorporate static information about elevation, for instance, to get the best prediction for the actual rain. This competition was organized by the Institute of Advanced Research in Artificial Intelligence with support and in partnership with AEMET, the Spanish National Meteorological Agency, the European Space Agency, ESA, and the Salesian University of Technology. Now, deep learning in weather prediction actually by now has a quite interesting track record. Although this is all fairly new, just a couple of years ago, the field discovered that deep learning can match or even outperform physical numerical models in short-term predictions of rainfall. Specifically, Agrawal et al. Showed that a simple unit architecture could effectively capture rain patterns for predictions up to 60 minutes. Incidentally, just after another IRI competition, traffic forecast, showed a similar success of units for traffic prediction when presented in image and video form. A few months later, Sønderby et al. Successfully already predicted rainfall for up to 8 hours using spatial-temporal encoders with axial attention. In September 21, Raevskiy et al. Published a paper in Nature where they not only show that generative models can predict rain across the United Kingdom, but that actually meteorologists prefer those predictions compared to competing predictions, including numerical models. Last but not least, Espehold et al. Showed that large recurrent convolutional networks with residual blocks can outperform operation models even up to 12 hours. This trend in improving predictions, however, is accompanied by a more unfortunate trend that these very large and powerful models are trained on data that are usually not fully accessible to the scientific community, whether that's due to licensing issues or a need for elaborate downloads and pre-processing of the data. I want to show here very briefly an overview of other existing data sets and to put the data that we release as part of Weather Forecast 21 and 22 into perspective. And you can see that most of the other data sets are many orders of magnitude smaller. Not only that, many of them have a much worse resolution, particularly in terms of time. I'm not going to dwell on this because most of you have actually worked on the data, but I want to give a little bit of an overview of the community that Weather Forecast has fostered and rallied around this competition task. In total, there were 30 teams taking part in the competition from over a dozen countries, and we scored over 1,600 submissions. 900 of those were actually beating the baselines, kind of indicating that this is not a trivial task. And we maintained over 250 leaderboard entries beating the baseline. These 1,600 submissions split into 1,100 for stage 1 and over 400 for a very challenging stage 2, for which delegates only had about a month to adapt their models to. This tight timeline is partly due to the difficulties of actually obtaining the data, and we're really grateful to our partners and support from AEMET who helped us put these data together. Anyone who has downloaded and processed large-scale data from raw satellite sensor will actually appreciate how tricky this is and how technically demanding. So we're very proud that we put this all together, and we're very excited that so many people of you took on this challenge even on such a short notice. The 500 stage 2 submissions split into 400 of the core challenge, 40 to the held out leaderboard, or I should say that actually submissions were restricted to a fixed number per team, 75 in the transfer learning, which is an even harder challenge, and 20 in the transfer learning held out. Perhaps to give a visual overview of how these submissions were scoring, you can here see the timeline on the x-axis and the score on the y-axis. And this is for the stage 1 competition. It's quite striking that some extremely well-performing models were submitted fairly early on, and that the winning submissions were actually not very close to the deadline. This is a trend that repeats itself. Here you can see where we closed the stage 2 core leaderboard so that people could focus on the heldouts. And here we reopened submissions so that people could play around some more while preparing their scientific abstracts. And again, the winning models are interestingly not submitted super close to the deadline, despite, of course, the very high activity close to this. To those of you who remember that the deadline was the 14th of November and see that there are still some submissions after that, I should say that the time shown here is not the submission time, but at the time that the score was computed. And actually computing these scores for these substantially large data sets for so many submissions can easily take several hours. And actually the November 14 here is the beginning of November 14. So that's why they look as if they were over. They were not over. Every submission scored and considered for the leaderboard was uploaded before the deadline. This is the corresponding plot for the stage 2 transfer leaderboard. Again, you will see some very good submissions well before the deadline, and these are the corresponding held out leaderboards. It is now with great pleasure that I introduce you to the first talk of the next session. Thank you very much, Pilar. So Pilar Ripodas will present an introduction to estimating and forecasting precipitation from radar and satellite meteorological data. Please from AMET, our key partner in preparing and enabling this competition. And Pilar, I very much look forward to your talk.
Okay, so thank you very much. And thank you for the introduction. So I will start already with the presentation. Precipitation is one of the most important meteorological variables, and it has a high impact in life and economy, as you can see in these extreme events in the pictures. And I will talk about measurements and estimations of precipitation, mostly during this presentation. This can be done with rain gauges, radar, or satellites. I will start with rain gauges. A rain gauge gathers and measures the amount of precipitation. And this is the depth of precipitation that occurs over a unit area, typically in millimeters or liter per square meter. And the intensity of precipitation is the amount of precipitation per unit time. We have two kinds of rain gauges, the non-recording ones. In them, water contained in a receiving bottle is measured by a graduated measuring glass. And these measurements can be done once or several times in a day. And in a recording one, what we have is records the amount of precipitation collected as a function of time. So we can say that rain gauges are real measurements of precipitations, but we know that precipitation has a large spatial variability. And therefore, a single point measurement is not very representative of a given area. For this, what we really need is a dense network of rain gauges. But even if we have a very good dense network, we still encounter some difficulties that can be the inhomogeneity of the sensors, the cost of the setting and maintaining this network. There are areas that are very difficult to access to, And of course, we have areas that are not covered, like lakes or other water areas cannot be covered. And then we turn to another kind of measurements that are done with radar. These measurements are also ground-based measurements that we can radar can scan in all the directions and at different elevations. And as we know, radars are active sensors, so they send out microwave pulse. And when one of these pulse encounter precipitation particles, then part of the energy is scattered back to the radar. And then the radar can measure the time between the emission and when it returns. And from this, we can have the location of the target, of the precipitation. And we also have the reflectivity, that is the amount of the transmitted power that returns to the radar after hitting precipitation compared to a reference. And this reflectivity is related to the intensity of the precipitation. So there are several relationships that can provide a precipitation from the reflectivity. And the most used is the Marshall-Palmer relationship. So here you can see an example of a radar. We can see how the radar with the beams at different elevations can hit the target and get back the signal. In this, it means I'm showing some of the problems that we encounter with radars. One is, for example, we have a mountain. The radar cannot see the precipitation behind the mountain. It will have drizzle with very small water particles. Then the radar cannot see it. Or sometimes, depending on the vertical profile of the atmosphere, we can find that sunbeams sent by the radar don't go up but go down to the surface, so we have false echoes in the radar. But even if we find some problems with the radar, we can say in general that a radar provides very good coverage even of close areas. And we can get the 3D structure of the precipitation systems, and we can also track the precipitation systems. So this is why it is widely used in the meteorological warning and nowcasting services. And it is often used as a ground truth. Here we have an example of a radar in Zaragoza in Spain. This is what we can do with a radar, but if we have a network of radars, then we can get a very good coverage, as we can see here. And now this is why I will talk about the Opera project from Eunbin. Most of the European Met services participate in this project, and the objective is to have a platform for expertise exchange, but also in the project they are producing in an operational basis radar composite products for Europe, as the one that we can see in the picture. So the Opera produces 2D composites for instantaneous surface and rain rate and maximum reflectivity, and also 1 hour accumulations. So we have provided for this weather forecast competition the Opera radar data, in particular the instantaneous rain rate, and these are considered as the truth in this competition. We are providing it every 15 minutes. And here I want to thank Anna Kaisa von Lerber, that is the manager of the Opera project, for her help to get the license to use the Opera composite data for the competition. And now I will talk about the satellites. It's another way of observing the Earth. Yeah, they can have a very, we can have globally image of the Earth. And satellites carry different instruments. Some of them are good for measuring precipitation, others not. And I will mention in particular the GPM constellation, because its purpose is the measurement of the precipitation. I think I will go to the picture. So this is the GPN constellation. So there is one satellite that is the GPN core observatory that has been set by NASA and JAXA, and it has passive and active microwave sensors and allowed to have a measurement of the precipitation, and at the same time are a good reference and can be used to calibrate the measurements of other satellites that have passive sensors on board. And with all these satellites, with combining the data of all of them, we can have, as we can see in this video, values of the precipitation. In blue is zero precipitation value, and in red is when we have high precipitation. As we can see with this constellation, we can have a global coverage, but the problem is that we don't have a good temporal resolution, and this is what we need for weather watching and nowcasting. And this is how we come to geostationary satellites. They are always observing the same area, and this means that they are good for weather watching and nowcasting. There are several geometeorological satellites, and with this one here from NASA, EUMETSAT, and JAXA, we can have a global coverage, as we can see in this infrared image. In particular, the Meteosat second generation satellite from EUMETSAT provides images every 50 minutes over Europe and Africa. It has 12 infrared and visible channels, and as it is a geostationary satellite, it's good for weather watching and nowcasting, but it doesn't have microwave sensors on board, and therefore it can only see the top of the clouds, and precipitation can only be indirectly estimated. An example of this is what we do in the Nowcasting SAF project for EUMETSAT. It is a consortium of Met services of Spain and other countries. We are providing software to generate satellite-derived products with application on nowcasting. In particular, I will mention the CRPH product that provides competitive precipitation rate. Its algorithm is based on principal components, and the radar data has been used as truth for calibrating the product. And here you can see an example of the radar measurement and what the satellite can provide. And now one slide about forecasting precipitation. Here I distinguish between lead periods from a few hours to several days. For this forecast, what is usually used are the numerical weather prediction models. I want to highlight here that precipitation is a diagnostic variable and not a prognostic one, and that the precipitation one is one of the most challenging variables for the models. And for the first hours, what we call nowcasting, what typically is done is to get very good observations and then to do an extrapolation of them. And other way of doing nowcasting is to use in general artificial intelligence models. And in this context is that we have collaborated with ERI to set this competition, weather forecast competition. And yeah, we are looking forward to the outcome of it. And yeah, I thank you very much for your attention.
Thank you very much, Pilar. We follow on briefly with an overview of the data characteristics by Alexandra Grutzev.
I will now give a short introduction about competition design and data. Most of you already work with the data, so you know this data set very well. But for those who maybe join us outside of the competition, maybe a few words how we prepared the data set and what was the main competition challenge. So As Pilar already mentioned, we used satellite data as weather forecast input variables. So she already described Meteo's UMETSAT satellite spectral bands. As the input data set, we had 11 spectral bands. 8 of them are infrared and 3 are visible. So they represent different types of the observations. And we also provided static variables, so latitude, longitude, and elevation. So these 11 channels were input variables of the weather forecast challenge. And based on those, we asked our participants to predict the rain radar rates. And again, Pilar already said a lot about how the sensor works and why they are so important. So I will just move now to the data preparation part. So the first thing before actually we created input data set, the first thing that had to be done was the projection of the opera data to satellite grid. And I would like to mention that we are very grateful for IMET for doing this, because there was a lot of preprocessing of this large scale data set. So the problem was that opera pixels are not aligned with the satellite grid. So what you can see here on the picture, more or less, is the green grid is a satellite grid. So the spatial resolution of the satellite pixels is much higher than the spatial resolution of the opera pixels, and this changed depending on which part of the disk we are. And basically, each opera pixels covers the area of 2 times kilometers by 2 times 2 kilometers by 2 kilometers, but it's different for the satellite pixels. So if you are closer to the disk, we can say, for example, in space, a satellite pixel covers area around 4.5 kilometers. But as we are moving more into the North Pole, then a satellite pixel will cover much bigger area. So even up to 12 kilometers by 12 kilometers. So the data were projected to align grids in a way that reduces the projection errors, and this is also why the spatial resolution of the satellite data is different than the spatial resolution of the opera data. So now going to the weather forecast competition task, the task of the competition were to predict 8 hours of the weather based on 4-hour input data. And these 4-hour input data were represented by 4 pictures. Each picture had 11 channels, which were satellite spectral bands. And based on this, we asked our participants to predict opera rain rates. So we gave the participants 1 hour of the satellite data as an input data. And because the satellite data comes in 15 minutes frequency, it was 4 images. And based on this, we asked participants to predict 8 consecutive hours. And because the opera data is also given with the frequency of 15 minutes, that was represented by 32 pictures or 32 frames. And here was the only 1 channel because we asked to predict rain rates. Regarding the spatial, the pixel, the resolution of the size of the prediction area, the prediction area was 40 times to 40 times pixel, so this was the input data set, and the output was the size of the image was 252 times 252. And in addition, we also provide a spatial context for the prediction. So the input data set also included additional context area. This size of this area was 252 times 252 pixels. This area surrounds the region of the interest, and then can be used by the model to learn the weather dynamics, because of course the weather moves over time. And the region of the interest, so this 42 times 42 pixels in satellite resolution that corresponds to 252 times 252 pixels in opera resolution, is roughly 170 kilometers by 170 kilometers, and the context is roughly 1000 kilometers by 1000 kilometers. And now the core challenge. The main weather forecast challenge, so the core challenge, was to predict rain events for seven regions in 2019 and 2020. We were calling those regions known. We call those regions known because for them we provided training and validation data set. So this training and validation data set included satellite spectral bands and corresponding opera rain rates, so the model can learn the patterns. And as I already mentioned, those information were given for each 15 minutes time slot. So that was the core challenge. And the second challenge, the transfer learning challenge, we have asked our participants to predict rain events for 3 new regions in 2019 and 2020. So for those regions, no training and validation data were given. We also asked participants for not only spatial transfer learning, but also for time transfer learning. So we asked participants for a prediction in a new period of time in the year 2021. And in 2021, we didn't provide any data for those regions. So just to summarize weather forecast 2022 challenge, this is a complex challenge because to build the good models, participants must solve many difficult problems. So first one is super resolution, because as we mentioned, spatial resolution of the satellite images is different than spatial resolution of the ground radar. So it's about 6 times lower for satellite images in comparison to the ground radar. Another challenge was data fusion, because to model ground radar rain rates, the participants had to fuse patterns from 11 visual and infrared satellite bands, and they could also use static data. And for transfer learning, challenge the participants need to build a model that's able to generalize both across space and time, because they need to predict the weather for new regions, unknown regions, and also in a new year for which they didn't see any training data. And finally, moving to the weather forecast evaluation metric. So we decided to evaluate weather forecast submission with the intersection over union metric. And for those who are already longer in the weather forecast community, so for those who maybe took part in the weather forecast 2021 competition, you know that we discuss which metric should be actually relevant to this challenge. Because actually this is the first time when such a data set is available, we decided to make a problem simpler. So instead of asking the participants to predict the actual rain rate, we asked them to predict rain event. So we provide binary mask for rain, no rain prediction, and we use 0.2 threshold for opera data for rain detection. We remove no data and no coverage values from the prediction area for the opera, because as Pilar mentioned, Opera, there are some regions that in the Europe that cannot be covered by Opera sensors. And Haiyu metric was average over all regions. And we decided to frame this task as one class problem. So we only evaluated detection of rain event. So thank you very much. That's all from my side. And now I'm really excited to see the solutions and to see how the participants actually solve a weather forecast challenge.
Thank you very much. The next presentation is by Team FIT-CTU and Meteor.
Hi. Hello. I hope you can hear us and see us and see our presentation.
Wonderful.
First, I would like to thank you for the opportunity and for all the data that you prepared for us and that we were able to be part of this very interesting, difficult challenge. I would like to quickly introduce us. We are a Faculty of Information Technology from Czech Technical University. We were 4 in the team. My colleague Jiří Pihrt is here with me. Rudolf, Raevskiy, and Matej, Choma are not with us right now. I would like to very quickly introduce meteoai, which is a company that works with us for a very long time. They actually developed their own radars, weather radars, quite successfully. They have more than 30 radars deployed and installed all over the globe. And actually, what I think might be interesting for this kind of challenge is that they are creating or developing their new radar, which is mobile. So maybe in the future it can be easy to gather data and gather training radar data, so we can use the satellite data for nowcasting or prediction in very remote areas where there is no radar available. So we have this team in Data Lab, which is a laboratory of data science, and we have quite a long history in weather forecast and using neural networks for weather forecasting. We started with, like you mentioned, with very simple units, then something more and more difficult. For precipitation nowcasting, we work on satellite nowcasting, post-processing of numerical weather prediction together with satellite and radar data, fusing all these things together. We are trying to solve problems of radar blockage by some in-painting, and here we share the links to our archive and GitHub, and also to our laboratory. Right now, we are for the precipitation nowcasting, we are using FIT-net, which we will describe later. Right now, it's used in production over Czech Republic or Europe on meteoai web pages, also linked here. And right now we would like to describe you what we did and how we did it, and I will move.
Hello again, my name is Jiří Pihrt. First, I would like to briefly describe the data we used, which we already heard previously, but we used 7 regions from 2 years. The satellite data contains 11 bands, 2 visible, 7 infrared, and 2 moderators. The interval between frames is 15 minutes. We have 4 frames input and 32 frames output. And both of the data has 252 by 252 pixels, but one pixel corresponds to different areas. You can see at the picture on the right, the region of interest with the target radar data is smaller than the satellite. So that adds some additional challenge because it's a higher resolution. And the 8 hours to the future is also quite a challenging task for prediction. The task of the competition, as you heard previously, is a binary classification. In stage 1, the threshold was 0, and in stage 2, it was 0.2. And on the bottom, you can see some visualization of the data, where the black or white rectangles highlight the region of interest, and we show 3 selected channels and the target. So now I would like to show you our architecture. So we have 3 networks which are all trained separately, using the data in different ways. Firstly, we have a FIT-net, which we used only on the satellite data. It is basically a recurrent network, and we use it to basically extend the input satellite sequence. Then we have a UNet, which is trained to estimate the rainfall at the current time step. So we train it with 1 input frame and 1 output frame, and then we apply it to all the 4 input frames independently. And then we take outputs from both of these networks along with the input sequence, and we flatten and concavate it all and fuse it in a final unit network, which gives out the final prediction. But this prediction is for the entire satellite area. So to predict the region of interest, we crop the region of interest and upscale it to the target resolution, and then we compare it to the target. So more on the satellite FIT-net. It is a recurrent network, and we use all of the 11 channels and the entire input length, so 4 frames. And we only predict 10 frames because of memory requirements, and it's quite difficult to train it on more. And below you can see an example animation of the prediction with 3 channels.
And maybe not all of you are used to this FIT-net or are accustomed to. FIT-net tries to somehow decouple physical dynamics from some unknown factors. It is based on this paper from Leguien and Tom, Disentangling Physical Dynamics from 2020. This model inputs the image, like satellite image. The image is encoded, and then the encoded image is sent to 2 different paths. One is something called file cell, which is a recurrent cell that described a bit more here, that tries to use prescribed filters that actually can mean partial derivatives, and use these partial derivatives as prescribed filters to get something like a physical insight into the data. Then we combine the derivatives into something that could be called partial differential equation or partial differential term, and then it's outputted. Then we have this conf LSTM, which is the correction cell, which should, in theory, be there to correct anything that is missing in the file cell. What it should do, it should again, in theory, increase or add some missing physics, add some structure into the images, some missing phenomena, and so on. These 2 predictions are later summed and decoded, and after this we have a new predicted image in next time step. We found out that this method works very well for standard precipitation nowcasting. The biggest improvement compared to UNet or standard methods like PRET-RNN or PRET-RNN plus, is that it gives us a bit more information about the physics that is used, but a bit more because these, as you can see here, these derivatives are used only on the hidden state, so it's quite difficult to say what actually this means, like in physics. But it helps us to keep the internal structure of the storms, or in this case, of the clouds. So we use this method with really good results.
Next, there is the satellite radar unit, which is, like I said, trying to predict the rainfall at the current time step. So it doesn't do any future prediction. It just predicts estimates the rainfall. So it uses the entire satellite frame. So 11 input channels. Final is applied on all the 4 inputs frame independently. So we have more information about the current rain situation in the sample. So the final unit, which concatenates all of the inputs and the input sequence, it needs to have 158 input channels for all of the data, and 32 output channels is all of the output frames. And then the output is cropped and upscaled, like I described previously, and the upscaling is realized simply with bilinear interpolation with 6 times factor. This is quite simple. We tried more sophisticated methods, but we didn't get any improvement. But there is definitely more research available on this part. With some results, we compare with a simple unit, but that unit also contains the cropping and upscaling. It just doesn't include the FIT-net and the satellite radar unit. So here are some training charts from the validation set. Here's a table from with the Haiyu metric on the validation data set and the held out leaderboard metrics. And you can see that the WeatherFusionNet performs better on the core challenge, but it performs slightly worse on the transfer challenge. We are not sure why exactly, but it could be slightly overfitted on with respect to regions. And we also compared to attention unit, which we also tried, but it performed worse. Here we see a graph of the Haiyu metric over time. So as you can see, it's quite good at the start, but it quickly decreases over the 8 hours because 8 hours is a pretty long time frame. Here you can see an example animation of the predictions. On the left there is the target sequence. In the middle is the prediction, and on the right it is the probability before the threshold. And in the probability you can see over time, as the model gets more uncertain, the probability gets more like gray in this color scheme. Can continue?
We used a single NVIDIA A100 GPU for the training. Different parts of it use different memory. The FIT-net was roughly 30 gig of memory. It took 20 hours. The SAT-2 radar unit took 20 giga memory, 5 hours, and the final unit was again something over 30 giga memory and took 20 hours on the 8100. We also gathered some lessons learned while doing this challenge. We found out that cropping and upscaling the unit output worked well. Even this easy method. We tried to use dice loss and focal loss. We found out that it performed worse than BCE. Positive weight in BCE was important parameter. We found out that using one model for regions was better than one model for each. We also tried to include a bit more physics using rotation invariant unit, which was more difficult to train and performed worse. We tried this small attention unit, which is a unit with attention blocks, which performed also worse. And we used different ways how to do this ensembling, and only the presented method worked well. We are thinking about future further improvements. We would like to improve FIT-net. Right now, FIT-net computes up to 6 order derivatives, which is a bit unreasonable from the physical point of view. So we are working on changing this. We are also trying to change the architecture of the FIT-net a bit, improve the model. Right now we have conf LSTM, so we can try to replace it by something better. What we think is quite difficult and important is to improve the internal structure of the storms and clouds, and it's quite difficult task. We are not sure if it's only the result of uncertainty in the prediction, or if this is actually connected to some deep issues in deep learning, like F-principle or spectral bias, by which I mean that we can, in theory, predict even the structure better, but our architectures that we use are not well prepared for this task. This can be connected to improving loss function, or we can use something cool like diffusion models. Further, we are also willing to go to uncertainty quantification because it should be quite easy with these models. We would like to add more physics into the models, but it's difficult to say what physics and how. One thing that we are trying to do is to use some symmetries because based on Nether's theorem, it should be doable to encode some physics by symmetries. Yeah. We want to improve downscaling. We would like to try to train the whole model end to end, and we also didn't use the static data, like topological latitude, longitude, in the training. And that's all from us. Thank you for your attention.
Thank you very much. Any questions from the audience?
I have. By the way, I'm named as NeurIPS 2020 competition. I have two questions, actually. One is, how much better you think your model would be if you actually could be able to predict all 32 frames with the FIT-net model?
It's quite difficult to train it on such a long sequence, but if it was good at it, then it definitely would be better.
But I think that it's not only a problem with the hardware, but I think that right now we can't really predict the satellite images for 8 hours. It just won't work.
But because of the complexity of the problem?
Yeah. Yeah.
Mm-hmm.
and chaotic behavior and all these things. So I think it's very difficult to do this correctly.
Okay, and if I may have a second question, and I have to say we don't know the answer for this too. Why do you think that using BC metric gave better results than IOU or dice loss? Have you thought about it?
Yeah, I think maybe. BC is slightly easier to train. It's easier for the model to fit the solution. It's just guess. It's, I think, quite difficult to say really what is the reason.
Okay, thank you.
Okay, thank you. Okay, I have a question on the chat by Dr. Kopp, and I saw Omid was raising a hand. So please feel free to just type your questions on the chat, then we can repeat them back and stay in schedule. So Michael is thanking you for your great talk and solution, and was wondering if you managed to have a look qualitatively at the output as to what using FIT-CTU and the second unit had on the output.
Yeah, we compared it to using to not using any of them. We didn't have time to do an ablation analysis if like using only one of them would be enough. But yes, it's definitely better than not using none of them.
It's difficult to qualitatively compare it because it's just ones and zeros, so you don't see any structure there. It's difficult to compare.
Okay, thank you. So there's another question by Michael Kopp about whether you use graded clipping in training.
We used it for the final unit because we used the baseline starter kit which contained this. I didn't do it for the FIT-CTU or the satellite radar unit, but I basically use the same hyperparameters as in the baseline.
Maybe if I can have one question, it's
Okay.
possible to, or what is the license of the data? If it's possible to use them for research or for students?
That's a good question. Well, the satellite data are free to use for research because they're modified data. They're not the original EUMETSAT data. For the OPERA data, actually, Pilar Ripodos might be the person best placed to comment on that because we received the OPERA data through IMET. Pilar, do you maybe want to briefly comment on the licensing side?
Yes. So the license we got for the OPERA data is for the competition. So it's just for,
okay.
I think it's for the competition, yeah. And also for the next competitions we can set, yeah.
Mm-hmm. So one thing we can do, what we've done with other competitions, is having an open-ended challenge where basically any papers that lead to insights from the data can be submitted to the competition track, and then that would allow you to do arbitrary research on the data, but still stay within the competition framework. So if there's an interest in this, please let me know.
Yeah.
Okay, if I may also add something, I think actually in our terms and condition, we already have this open competition part.
Yeah.
So basically, I mean, you can go and actually see how this looks like, but if you accept the terms and the condition of the competition and you use those data set in the frame of the competition, which, as David said, means getting out the paper out of this and making this really available. So as long as this final or end, or let's say after NeurIPS stage is open, it is possible.
Yeah. So basically that would mean that you need to share your results with the competition community by publishing the results in the next competition setting. And after it's been presented there, it can of course be published in other venues as well.
Okay, thank you very much.
Cool. Okay, so I think that it's time to move on. I would have had another question, but maybe we can keep this for the discussion session. So thank you very much. Can the next slides please go up already, perhaps?
Okay.
Great. So Haiyu will present on super resolution probabilistic rain prediction using 3D units and EarthFormers. Haiyu, stage is yours.
Yeah, I'm Haiyu from Microsoft. The other team member is Liang from Nanjing University of Information Science and Technology. Next, I'm going to present our solution of this competition. This task is to predict rain events 8 hours into the future from 1 hour sequence of satellite imaging. As we are already familiar with the task, we will not talk much about it. Okay, since this is a deep learning task, we started with model. We tried a number of different spatial temporal models, and it turned out that 3-dimensional unit and also EarthFormer are at the top. For this 3-dimensional unit, it's an encoder-decoder structure. It consists of 5 encode block and 4 decode block and 1 output block. For this task, we added an ensemble layer and also a sigmoid function to output the probability of the target size, same target size. The other model we used is EarthFormer, and it was recently published this year. From figure 1, we can see that the EarthFormer is a hierarchical transforming encoder, decoder based on cuboid attention. From the second figure on the right, we can see that the cuboid attention layer has 3 steps: decompose, attend, and merge. First, the input spatial-temporal tensor is decomposed into a sequence of cuboids. Second, the self-attention within each cuboid attention layer is applied. Finally, the sequence of cuboids are merged back to the original input shape. The merge step is the inverse operation of the decompose step, due to the fact that the cuboids do not communicate with each other. Each cuboid is not capable of understanding the global dynamics of the system. Therefore, the elements will not only attend to each element within this cuboid attention, but also attend to the global vector on the right. Each cuboid is performing with the global vector with the self-attention. As for cuboid decomposition strategy in figure 3 on the bottom, there can be multiple options: local, dilated, shift, or non-shift. The previous 2 slides are about the models we used to model. Here is the improvement strategy that we made. The first column is the strategy, and the second column is the model performance gain by IOU. Next, I'm going to go through each of the strategy. Spatial context of the satellite input is one of the most important data strategies that we explored. Generally speaking, this is the balance of more information and the relevant information that we input to model. After investigation and experiment, we used input context of 126 by 126, which is about 3 times the target spatial context. And our finding is also consistent with the finding in paper of Google's MetNet2. The left screenshot is the input and the target of the spatial context in MetNet2. When the model predicts 12 hours of precipitation, the input size is 3 times of the target context. In our task, we predict 8 hours, so our context is 3 times of the target. What's more, we actually explored more about the spatial context. We compared different spatial contexts. Here are 3 typical examples. 42 by 42, the green line, means the same spatial context of input and target. 126 by 126, the orange line, 3 times of the target size, while 252 by 252, the blue line, 6 times of the target. In first 2 hours, 42 by 42 performed the best. But in long times, 126 by 126 performed better. However, interestingly, 252 by 252 is not better than 126. This indicates that it's not the larger, the better. Let's put it another way. If we feed the model with more than it can learn from, the result will be worse, even though the 126 input is already included in the 252 input. Interesting. As for model input, besides the spatial context, we also explore the cell life channel. We use the permutation test to analyze the effect of each cell life channel on the rain prediction. For each individual experiment, we randomize the one input cell light channel on all of the samples and all frames on the validation set. Then we evaluated the result. If the matrix score drops, then the randomized channel input has the positive effect. The more the matrix drops, the more important the randomized cell light channel is for the prediction. And the results show that cell light channel IR 087, 134, 108 are the best predictors for rain prediction. And also cell light channel of water vapor and the visible also have influence. We also tried a couple of loss functions. Or for IOU, we can think of it as the CSI. As for dice loss, more weight is put on the true positive, which means that we care more about hit rate. Focal loss considers more about the heavy rain event. We found that IOU loss, dice loss, and also focal loss are all better than BCE loss. And this should be due to the imbalanced data distribution, the imbalanced rain data distribution. In order to make better use of the advantage of these three loss functions, we tried different combinations, and it worked as expected. The combinations all provide obvious improvement. Finally, we use the two combined loss functions to train the final model. It's natural to ensemble a couple of the good models to produce the better result. We assembled 4 models, 2 3-dimensional units with different combined loss functions, and 2 EarthFormers with similar IOU loss, but with different initial downsample stack layer. These 4 are the top models with diversity. From the table below, the ensemble solution provided obvious performance gain. When converting probability to binary, rain or not rain, we found that different regions have different optimal threshold. So we searched optimal threshold range for each region to further improve the performance. The figure shows that the metric IOU distribution with different thresholds at each region. We also checked some precipitation event. From this typical example, we can easily say that all models have difficulty in predicting local small-scale precipitation, as I circled here, especially for long lead times, such as after 3 hours. But all models have better forecasting skill on continuous and widespread precipitation. To conclude, we assembled 3-dimensional units and EarthFormers to achieve the second place on this particular contest. A few of the things that help to improve the model performance we explored, including spatial context, loss function, threshold optimization, and also the feature importance of each cell light channel. Actually, we didn't use the static data, elevation, longitude, and latitude. In our experiments, it did not work as expected. So finally, we didn't use it. And this is also consistent with some findings in the DDMR model, the paper, the Nature paper from DeepMind last year. They didn't use the static elevation data, longitude and altitude data. Especially in the workshop, in special session of last year, they also talked about it. Okay, that's it for our team. Thanks.
Thank you very much. Are there any questions from the audience? Okay, I have a first question. I like how you looked into what the different losses and the different variables contributed to your solution, and that you were optimizing this also by region. How can you then carry forward this type of model performance, if you like, to new domains in terms of space and time? I mean, if you see that there are parameters that are clearly so region specific, how can you then have a forecast that also works in other regions?
So your question about loss function?
Mm-hmm. Well, more generally, you really optimize your model also in terms of performance on each region, where you say you pick different thresholds because different thresholds work better for different regions. How can the model then flexibly adapt to new regions?
Oh, good question. Really good question. So we explored and detected the optimal threshold range for each region. Mm-hmm. And for each region, we can pick the optimal threshold within this range. Mm-hmm. And then it will work well. After we tested multiple submission or multiple test results in offline, mm-hmm. And we also found within the optimal range, it can perform well. Okay, so your question is the new region that the model did not see, mm-hmm. did not see, right? And based on this optimal region, and we come up with some suboptimal region for better general purpose. And based on all this, we can get good result. Finally, when we got second place on both the core and also transfer learning leaderboard, we got second place. This is one of the finding that we perform stably on both the core offline and core and transfer learning. Also, another thing that can ensure a stable performance is the model ensemble. Okay, so the ensemble basically takes care of this. Okay. Yeah, it can very much ensure. I mean, as I mentioned earlier, we have two three-dimensional units with different loss function, and two EarthFormers with I didn't mark here, with different input initial downsample layer. And then the four models have diversity and all perform well. And then when we ensemble them together, and the final result is good, is better. And also, due to the diversity, it has better generalization capability on new region. Okay. Okay, thank you very much. There's a question by Brian Pulfer, who says, thank you for your presentation, and he would like to ask which optimizer did you use in your experiments, and how did you weight the different losses? Weighted the different losses, or we just combine the loss function in training? Yes, and I think the question is, how did you weight the different loss functions in this combination? Did you weight them equally? Did you just take the average loss of these three, or did you weight them in some way? How did you determine the weights? Oh, very good question. Okay, so this is also a question for the ensemble strategy. When we ensemble multimodal, we can also do an average and also weighted average. The same issue here for loss function. We tried weighted and also just the direct average. The difference is not obvious. So we use average. This also reminded me one paper, if I remember it correctly, early this year or end of last year, that a simple average of multiple models perform better than transformer on the Eunbin net. The interesting paper. Thank you very much. And what optimizer did you use? Optimization. I didn't put Adam.
Okay.
Yeah.
Okay, are there any other questions from the audience? If not, then thank you very much again. And I would like to move to the next presenter because we're running a little bit behind.
Okay.
The next presentation is by Brian Pulfer.
Yes.
Wonderful.
Okay, perfect. Then without further ado, I would like to present to you our solution to the weather forecast challenge. So my team is composed by myself, Brian, Yury here just next to me, and our teammate Sergey joining us online virtually. And today we have the pleasure to present our solution jointly. So, okay. So we've prepared some slides introducing the challenge just in case we would reuse them to introduce someone that is not familiar with the challenge. But since you gave already such nice presentations before, I think I would just skip through these. I think most of us are familiar with the data and with the problem by now, and also with what the model prediction looks like and what the goal is. So, and also, of course, the metrics used for scoring the submissions. So without further ado, I would start with actually our last implemented model for this challenge, which is just an adaptation of the Vivid model, a video vision transformer. So if you know the paper, this image will be very familiar to you. If not, it's a very simple architecture. In the actual paper, there's multiple ways to, the author proposed multiple ways to do video classification. So it's originally an architecture for video classification. And this is one of the ways they propose to use transformers for doing video classifications. So, by the way, we are using transformers in all of our implemented models, motivated by the recent success in the field of computer vision. And so this is the last model we tried for this challenge. The idea is very simple. We treat the input for this challenge, and we try to treat it as a video. So we're given ideally like 4 frames, each of which has 11 channels and a spatial resolution of 252 by 252. And we apply separately to each of these 4 frames a spatial transformer model, so just a shared transformer model, which for each frame will give a class token. And then after that, we collect all of these class tokens from each of these 4 frames, and we feed them to another transformer, which goal now is to capture the temporal information between the frames. And this finally, in the original Vivid architecture, will give you a final classification token, which you can then use for your downstream classification task. In our case, it's a bit more complicated than that, because if we interpret the input as a video, then the challenge is a video-to-video prediction. So we cannot just output the classification token. Instead, we have to use it to come up with the actual solution. And the top yellow box you see here is our adaptation with respect to the Vivid model. We simply take this classification token that the model outputs, and we run a very simple spatial interpolation to go back to the resolution required for the prediction. And we finally apply one more convolution to get the final prediction. So this is not exactly probably the most optimum way to go about it, but we were a bit short on time, And despite the simplicity of this approach, this model is very close to the baseline. It's slightly inferior in performances, but it's quite close to the baseline already. And so we've included it in our paper and in our code because we suspect that this idea, this concept can be in future enhanced in future work. And so now, without further ado, I will leave the word to Sergey to tell you more about the second model we've experimented with.
Yeah. Hello again. So as it was already mentioned, we have a three-dimensional data in this task, and one of the few other fields in computer vision is medical image processing, where three-dimensional data is commonly used. So it seemed pretty natural to try best models and best architectures from this field. One of the latest best models in this medical image processing task is Seungheon architecture, which was applied to predict brain tumors on medical images. In this architecture, the input data firstly processed by Swin transformer, and these outputs of Swin visual transformer is fed into different layers of UNet architecture, which stands as decoder there. And before feeding to Swin transformer, the data is processed to create non-overlapping patches and windows to compute self-attention. However, we need to adapt this model for the weather prediction task. So first of all, please move to the previous slide. Yeah. First of all, this model worked with the same dimension, so there was no any super resolution or just moving in time. So we needed to find a way how to adapt to this. So the most straightforward way was to just repeat the input data in a time channel. We look at the time channel here as one of the spatial dimensions. So just repeat it 8 times each and get 32 shaped tensor as the input to the Seungheon error model. And we basically output the same dimension except channels. However, it was not the only way to process this data. So we also tried different approaches to this. The already mentioned repeat interleave approach performed better than others, but I would like to mention them. So we also tried channel convolution. So we just added a few convolutional layers before the input to the Seungheon error transformer to get the desired dimension. And also we tried to alter an architecture of the Swin transformer a bit. So we had on the last layers of UNet, we have co-transpose that upsamples the channel that we want to sample. However, these approaches didn't work well enough, and it seems at least a bit natural why. So one of the guesses is because of repeat interleave just like repeats the data, as we don't need to learn some weights or some function that needs to upsample, because it's not the upsample task in nature. Yes, so also I'd like to mention that we tried to train for minimum 4 epochs for each of the approaches. It's not too large, but too long, but this model is quite big, and it was quite hard to train for it. So basically, we had a batch size of 7, but we tried to find ways to speed up our training. Please move to the next slide. Yeah, so the basic training in 32-bit was remained the same results as if we also try to train in mixed precision mode or 16-bit mode. It outputs the same results as the original one. So there are ways to improve this, and there are ways to speed up things a bit, because this model is not easy to inference or train. So I think my colleague Yury will continue our presentation about other approaches. Thank you.
Okay, welcome everyone. We also explored several ways of improving the official baseline. This includes using an attention rate, changing the activation function from ReLU to randomized ReLU, which can be used as a parametric version of leaky ReLU, where instead of the constant negative slope, it's randomized, and also the changing normalization from batch to instance. It is also well known that transpose convolution would produce checkerboard effect. That's why they are often replaced with the regular sample operation and the standard convolution layer. We also tried the same. Baseline improvements tend to boost results, and the replacing transpose convolution isn't too significant. But still, these two models perform better than the official baseline. Also, we want to present a model-independent configuration that can be applied to almost any model. And the first one, we explored different losses. Surprisingly, optimizing the target metric intersection over union leads to worse results. And this holds true for both baseline and swinging and interim models. And for us, using causal loss function, such as combination of DAS and Poco loss, also does not improve performance. The best results were obtained using the binary cross-entropy loss with the weight of positive examples computed from the training set. A disparity between the training and validation data set may result in suboptimal model choice. For instance, for one of the regions, Roxy 7 in 2020, the mean and the maximum rain rates at training and validation sets differ by almost a factor of 2. Maybe that's why on the held out data set for this region, the scores were the worst. To tackle this mismatch, it is possible to treat the full validation set as a part of the training plan and to train on more samples. However, adding a validation set, data set slightly improves their overall metric, but comes at the cost of making the validation metric inconsistent. This is no longer possible to rely on this score for model selection or early stopping, and which may lead to overfitting, which shown in the last row that the same model, when trained longer, produce really bad results. When deciding the output of class 4 prediction of a model, we need to choose a threshold value for its output above which is region classified under as rain and vice versa. We experimented with the different threshold values ranging from 0.2 to 0.7, and both lowering or increasing the threshold for rain detection results in poor performance. Maybe as in previous solution, we need to choose threshold for each region individually and not one global threshold. Also, during the test stage, we computed a lot of the submissions, and we decided to combine them using the majority voting approach. What is it? First, a prediction of different models are generated, and the final prediction for each pixel is determined by the most frequent options. That is, if the most model predicts that it will rain at a given place at a given moment, that will be the final prediction, and vice versa. And we can see that the majority voting approach outperform each based on individual model. And in our approach, we tested with all 50 models, even the not suboptimal ones for the test data set. And maybe if we exclude more models, the performance could be further improved. Unfortunately, we didn't have time to test all our ideas properly, but for the future work, we want to change the optimizer from ADME to ADBelief following the last year competition winners, and also to enforce the temporal shift in our task, and to predict, it is possible to predict time deltas starting from the second time step, meaning our prediction at time step E is just a cumulative sum from 0 to E. And since we are dealing with different regions, instead of training a model for each region, we can use an embedding, and it can be an embedding either for the region or time embedding. It can be a year embedding, season of the month, because during winter the rains are highly less likely to occur than during the spring. And also deal with the data to mask some missing measurements and so on. And here are our results for the held-out split. Once again, was Sweden Netter and improved baseline performed particularly better than the official baseline. And majority voting approach significantly outperforms each of the model individually. As not only overall metric, but also values per region are shown to participants. A straightforward way to improve their score is to take the best prediction for each of the region individually and combine them into a new solution. This approach is shown in the last row, and it reaches the third place on the test leaderboard and the ex-aqua place on the held-out leaderboard. So in this presentation, we presented how we tackled the weather forecast competition. We first introduced a set of configurations that can apply and enhance result for almost any model, as well as baseline-specific improvements. We then proposed two approaches based on visual transformers: the interpretation of the input as a video or as a 3D medical image, and the use of problem-specific vivid or swing-net transformers. As in previous years, we reported that several different trained models yield the most competitive results, and our selected algorithm has placed X-Aqua third in the competition final, which suggests that the use of the transformers for weather prediction is a promising research direction that needs more investigation. The code, weight, and paper for our solution are publicly available, and thanks organizer for such a nice challenge, and thank everybody for attention. And do you have any questions?
Thank you very much. Alexandra?
Okay. Have you maybe tried to submit to the leaderboard the results from the model that was trained on higher threshold?
You mean this one?
Yes.
Yeah, we submitted onto the test leaderboard, and it's exactly the same model, just the generation script was running either with a 0.5 threshold or with lowering and increasing, and we had the submission, and significantly the scores were worse.
Worse. Okay, thank you.
I have a short question. What do you think would need to be done so the model generalizes better for transfer learning?
Thank you very much. It's actually a good question. Honestly, it's remain open for our research. It's maybe no, I don't have a particular answer right now. Sorry.
Okay. Well, area for future research. Okay, thank you very much. Then we would like to move to the next talk, please. So the next talk is by Minseok.
Hello, my name is Minseok of Team SI Analytics. I'm glad to present our work, simple baseline for weather forecasting using spatial-temporal contact aggregation network. The first presentation is about the model of our team solution. And later there will be another presentation on the learning method of our model. Let's begin with the first one. The three things we focused on when designing the model were low GPU memory, low computational complexity, and simply effective architecture. It is because weather data is usually very large, and the training model with a lot of GPU memory and computation are very time-consuming and costly. Also, we wanted to create a model with a simple architecture so that someone doing follow-up our research could easily modify each component of the model. Existing deep learning-based weather forecasting model include many components. For example, MNET-V2 study by Google is a hybrid structure that contains so many components such as conv-LSTM, conv-residual, and real-time embedding. MNET-V2 has inspired and contributed to researchers studying deep learning-based weather forecasting. But with so many components mixed all together, it's not clear which one are essential and which one are not. The complexity of this kind of structure is also a pain point for researchers studying the weather forecasting as they try to change the structure by projecting their idea. This is the EarthFormer. It is composed of convolution, transformer, and global vector embedding. It achieves state-of-art performance, but it also complex in architecture. Recently, a structure called SimVP has been proposed to solve this complexity problem. The model based on video frame prediction usually have low performance in novel view or distribution. Therefore, when models based on video frame prediction are used in the real world, their performance drops significantly due to their poor generalization performance. Our model was designed by converging various technologies to solve this problem. First, we use a technology called matrix decomposition for a small amount of GPU memory and computation. Decomposition technology is technology that has recently been spotlighted in computer vision and achieve high performance despite a small amount of computation. Also, we had a lot of transformer structure in mind, but we decided to use only pure CNNs because we want a simple structure design. In addition, since multi-stage training is complex and take a long time to train, we choose a structure that can be trained end-to-end fashion. Finally, our attention mechanism was used to obtain simply at powerful performance. This is an overview of our CNNet. CNNet consists of unit-based backbone model and spatial-temporal refinement module. The unit-based backbone model consists of large context aggregation module to improve performance and reduce the amount of computation. And the spatial-temporal refinement module serves to refine the prediction output from unit. One thing to note is that although it is refinement module, it is trained in end-to-end fashion. I will explain the component and their influence in detail. The first thing we tried was to train a unit baseline and measure its performance. When we validate the unit 3D baseline on stage 1 dataset, we got a 33.8 IOU. However, since the threshold of baseline unit 3D was 0.5, we changed the threshold of unit 3 to 0.6. Even though we simply adjust the threshold value, we were able to obtain a 2.1 IOU improvement result. Also, as in MNET-V2, the size of the input is 6 times larger than the size of the target lesion, so we cropped the center in the prediction result. After that, the size was adjusted through trilinear interpolation. When the center crop method was applied to unit 3D, 4.3 IOU improvement was obtained compared to baseline. These experimental results indicate that the center crop technique is very important in weather forecasting. Next is the refinement module. When we apply our proposed refinement module, we were able to obtain a result that was 8.0 IOU higher than the baseline. When the baseline was modified up to this point, it performed better than the EarthFormer. We tested on stage 1 data. Although the experiment was not conducted in the exact same setting, this experimental results show that high performance can be achieved in deep learning-based weather forecasting, even with simple structure. The motivation of the refinement module is strong spatial temporal correlation exists in weather. For example, as shown in the figure, if it rains in all surrounding timestamp, it is highly likely that it will rain in middle timestamp as well. Also, spatially, if it rains on all pixels around it, then the pixel corresponding to the center will be also have a high probability of rain. Therefore, we propose a spatial-temporal refinement module that can refine prediction result by aggregating spatial-temporal correlation. The spatial-temporal refinement module has a large receptive field, so it should be able to capture long-range dependency and require a small amount of computation. Therefore, we adopt large kernel attention method that can meet these requirements. Large kernel attention is a module that has achieved state-of-the-art using network decomposition. As shown in the figure on the left, it reduces the amount of computation by decomposing the large kernel into general convolution, dilate convolution, and depth-wise convolution. The figure on the right is the refinement module. The refinement module consists of large kernel attention module and 2 sequential residual blocks. However, since the existing large kernel attention module does not have time axis, we simply decompose the existing large kernel attention module to the time axis. Finally, this is the large spatial context aggregation module. When changing it to basic block of UNet, we were able to obtain a performance of 44.3. This performance was achieved by purely modifying the network. That is, we did not change any training strategy. Large spatial context aggregation module uses decomposition technique in all parts. It does not compute the spatial and temporal axis using a single convolution. It is an independent operation for each timestamp by utilizing spatial convolution. Then the output channels are divided into 4. It is calculated those kernels with different receptive field with spatial convolution, and then concatenated. Then time axis modeling is performed with temporal convolution. Finally, the information obtained spatial temporal decomposition is aggregate 3D convolution. So this procedure Šimánek can consider multi-scale picture. It is an overview consider only the spatial axis to simply express the large spatial context aggregation module. As shown in the figure, it is convolution operation that can consider various receptive fields at once. Unlike the large kernel attention, our large spatial context aggregation module does not compute attention operation. That is, we only use decomposition operation. This is a general formula for calculating flux of convolution. When the receptive field size is 27, the amount of computation is calculated as this figure. The computational load of our large spatial context aggregation module is reduced because everything is decomposed as shown in the red add sign. As a result, we are 30 times faster than normal convolution. This is an experiment comparing flux and parameter of UNet 3D baseline and Šimánek according to initial filter size. Transformer-based architecture have a very large amount of flux at less 4 parameters. However, Šimánek not only had few parameters but also very few flux. This flux means that it takes up less actual GPU memory, and there are various advantages such as training speed and large batch size. This is the experimental result. Our Šimánek achieved state-of-the-art stage 1 test dataset. And we also achieved state-of-the-art in stage 2 test dataset, but in the held-out set, we finished third. However, our Šimánek shows similar performance without significantly performance deviation in validation set, test set, and held-out set. This experimental result means that Šimánek has very good generalization performance. Also, state-of-the-art was achieved in both core transfer test set and held set. We got first place on 4 out of 5 leaderboard without any ensemble or fine-tuning. This is a qualitative experiment result. The green area of the ground truth is the area where the rain rate threshold is 0, and the yellow area is the area where the rain rate threshold is 0.2. As shown in the figure, Šimánek predicted as if the rain rate predict 0, even though it was trained with the rain rate set to 0.2. In our future work, we plan to add a rain rate regression task to Šimánek to mitigate this problem. Here's another example. As shown in the figure, Šimánek did a good capturing the movement of rain cloud from left to right. This experimental result indicate that Šimánek has the ability to model moving direction of cloud. This is a conclusion. First, we propose a weather forecasting model using low GPU memory. And we propose a weather forecasting model with low computation. Next, we propose a end-to-end model consisting only of pure Šimánek. Last, we achieve a state-of-the-art result without multi-modal ensemble or fine-tuning. But we could not increase the parameter of Šimánek or hyperparameter tuning because of the lack of GPU resource. In our future work, we will optimize Šimánek. And our research is not an architectural study, but a study to find out what factors should be considered when designing a model in field of weather forecasting. We hope that elements such as decomposition technique, refinement module, and center crop found in our research will be widely used. Thank you for your attention.
Thank you very much.
Sorry, one from me. Okay, so first I wanted to say that I really enjoyed the naming of your models on the Haiyu leaderboard. And anyone else who's curious, you can go to the Haiyu leaderboard and check them. And I have a question about the weights for your loss that you have been using for training. So what were the weights? And actually, did you try different weights or you just pick some values?
Okay, thank you for your question. We use a simple binary cross entropy loss, and positive weight is set to 4.
But on your slide, one of the slides, didn't you have the loss that was combined of 3 different losses? This loss presentation on next presentation. Our team solution is this presentation is our model, and next presentation is training stretches. Yeah, this is later. Okay, so I think the previous slide, yes. So next one, yeah. So you have the total loss, yeah, and you have here different components of it.
We have not experimented each component evaluation study, but we sequential add ours component. We believe each component is better result to all architecture.
Okay, thank you.
Yeah.
Thank you. Are there any other questions? And perhaps you can shed some further light on the inner workings of your models and your thinking in the next presentation by your team member. The next presentation will focus specifically on transfer learning. And it's actually been quite interesting to see that in this talent, different teams have won in the transfer learning talent compared to who won in the core talent. because we have seen that in past competitions, sometimes the leaderboard ranks agree very much, indicating that a model that predicts better in general also generalizes better. But in this particular competition scenario, the domain shifts are considerably stronger than we've had in past competitions. And that shows that models that can cope with this challenge can sometimes be structured a bit different to models that generally perform well in the core challenge. All right, Doyi, are you ready to present?
Yeah, I'm ready.
Excellent, let's go.
Yeah, okay, thank you. Good afternoon, everyone. Thank you for attending today's presentation. My name is Doyi Kim from SI Analytics, and originally Yeji Choi would be a presenter for this presentation, but her flight schedule was changed, so on behalf of her, I'm gonna do this presentation. Our team participated in the Weather4cast 2022 challenge and won the first prize in the core transfer stage. Today, we talk about a domain generalization strategy that is robust to spatial-temporal shift. This presentation will focus on how we solve the transfer problem, considering both atmospheric and computer vision science. Yeah, as you know, the prediction of rain cloud, the main object of weather forecasting is not a simple problem because they move their position with time and change their shapes irregularly, even sometimes splitting and merging. Many researchers have recently shown advance in deep learning-based weather models, but they still have some limitations. Especially data-driven models are very subject to noise and spatial-temporal properties in data. And these troubles are the inevitable properties of atmospheric observation data. Similarly, the weather forecast challenge aims to predict future rain events with past satellite and later data. Thus, we aim to build a deep learning-based weather forecasting model that is robust to spatial-temporal shift. We devised 3 strategies for CNET, our model, and introduced it here. In particular, we try to deeply understand about the atmospheric data. At first, we analyzed weather forecast data set. The satellite data from EUMETSAT consisted of 11 channels, such as visible infrared and water vapor band. Ground layer data from Opera Weather Network gives reflectivity-based rain rates. The catch here is that both images have the same pixel number, but different spatial resolution. The later image is located in the mid of the satellite image, which means that the legend to be predicted has a higher resolution than input satellite images. Also note that the legends studied are all different. We used the data from 7 legends for challenge stage 1 and 2, and 10 legends for stage 3. Since meteorological data reflect the other topographical characteristics of the target legend, this should be considered when testing another legend with a trained model. Next, we define the problem from the data set. The first problem is the spatial-temporal shift in data. Here, the difference in distribution between training and test data is usually called domain shift. Also, learning well in any domain with different distribution is called domain generalization. This figure shows the visualization result of spatial pattern from the later data set. Color bar indicates the frequency of the rain and no rain classes. Closer to yellow means a high frequency of rain events, and closer to blue means a low frequency of rain events. The results show different spatial patterns legend by legend. Therefore, we learned that this data set has spatial distribution shift in each region. However, performance degradation will inevitably occur if the training and test regions differ. We need to solve this for high performance. Additionally, we analyzed the 2090 and 2020 data set to confirm the temporal shift by region. So in figure, left side is the 2090 data set and right side is 2020 data set. However, the results show no apparent shift between a newer data set. It might be that 1 year is not enough to confirm temporal shift. Therefore, we are not considering temporal shift in this challenge. The second problem is a spatial-temporal correlation. General deep learning-based classification model use cross entropy, but it cannot consider the correlation in the dataset. However, most weather events have strong temporal and spatial correlations. For example, if it was raining 10 minutes ago, it is very likely that a particular point along the wind will also rain. Simultaneously, we can also find rain signals from physical trend over time, such as the gross velocities of cloud tops. Therefore, we need a loss function that describes these spatio-temporal correlations. So briefly summarized, here are the challenges and the approaches we propose in CNN. Geometric augmentation ensemble mitigated the spatial shift, and the temporal shift was not considered. We developed and used the spatial-temporal smooth loss to consider spatial-temporal correlation in weather events. Now, let's move on to its solution. The first is the augmentation policy that we propose to serve spatial shift. Computer vision recognition tasks commonly use various data augmentation policies to improve model robustness for domain shift. For example, there are geometric augmentation methods such as rotation, flip, and crop, and photometric augmentation methods such as blur and jitter. These represent augmentation policies significantly contribute to the general vision task. However, these are policies suitable for general RGB images. The data observed by meteorological satellite have mostly observed the radiation emitted by the atmosphere and are usually converted to temperature or albedo values. This means that applying the aforementioned policies to actual physical meaning can cause problems. The light figure is a result of applying auto and random augmentation. We can see that the geometric meaning of the original image has also disappeared. In that, unlike typical vision tasks, the same augmentation policy cannot be applied when using weather data. It should also be considered that a standardized policy is not available for weather forecasting problems in the full region. Therefore, we propose a new policy to augment data while preserving this meaning. One of the key points in this challenge was that the training region was wider than the target region we need to predict. In other words, it means that considering the cloud movement is helpful information for predicting future rain. Cloud movement is highly correlated with wind direction, so we devised our policy based on the wind direction in the target area. We analyzed the prevailing wind in the target region with optical flow. The prevailing wind appear as easterly and northerly wind. You can find green arrows in figure A. From B to D, the figures are the result of counterclockwise rotation by 90 degrees each. Even after rotation, the main wind direction is maintained in B and D, but are all changed to the opposite direction in C. This means that augmentation policy can reflect the movement of cloud or water vapor differently. This is the final augmentation policy we applied in this challenge. It is said to prevailing wind was preserved. The policy was optimized for our weather forecast data, but may change by legend change. Also considering the inherent physical meaning of weather data, we are not using photometric augmentation. Next is the geometric augmentation ensemble. In vision tasks, ensembles are mainly used to stabilize model result, but they are also used in numerical weather prediction models for the same reason. However, meteorological data is used and requires a large computational cost to create multi-models. Therefore, we propose a geometric augmentation ensemble that can obtain the effect of an ensemble with a single model. This ensemble augments the input image with our augmentation policy and then reversely augment it again. These are possible because we have defined and learned our own augmentation policy. Finally, the smooth loss. In general, pixel level classification problems use cross entropy, but they don't consider the spatial-temporal correlation of weather events. The figure is an example of the ideal prediction case. When the model outputs the same confidence in red and green pixels, the losses are also the same. However, the lead pixel is close to the actual lane area, while the green pixel is very far from here, almost middle of a clear area. Here, can we say that the two got equally the same loss? This is another example. The green pixel is harder to predict correct answers than the lead pixel, given their correlation with surroundings, because it's on the edge of the cloud. However, since we only consider pixel confidence, the same loss is calculated from cross entropy. The lead pixel should be given a larger penalty than the green pixel for the mispredict. Later, considering the surroundings, the green pixel is not seen as an entirely wrong prediction. Therefore, we propose spatial smooth loss to solve these problems. The middle green pixel has a relatively small loss by considering the surroundings. On the other hand, lead pixels should have high confidence considering the surrounding environment, but they don't. So we have to penalize them with a large loss. This is the concept of spatial smooth loss. Note that the counter size is fixed here, 3 by 3, but it is a hyperparameter that needs to be adjusted according to the spatial resolution of the output. Also, the temporal smooth loss is an extension of spatial loss on the time axis. As shown in the figure, if it rained all the way from the past to the future from the same location, there is a high probability that the central pixel will also rain. Therefore, the final loss considering both spatial-temporal correlations is the same as above. This is the result of applying the above proposal. We conducted an ablation study to confirm that each proposed approach helped improve CNA performance. Table 2 showed that our performance improved when we applied our spatial-temporal smooth loss and augmentation polish and geometric augmentation ensemble. The performance improvement was almost the same for each solution. Table 3 on the right is a comparative experiment about augmentation polish. We find that the performance is highest under our polish compared to the random and inverse policies. Using the inverse polish showed latter less performance than the base model. This shows how important it is to consider the correct geometric meaning. Finally, our model CNet showed the best performance without any model ensemble or fine-tuning with testing of the core transfer test and held out dataset. This is the final part, summarizing our contributions. We proposed a data augmentation polish based on the wind direction of the target region. We suggested a spatial-temporal smooth loss to consider the spatial-temporal correlation of weather events. Finally, we achieved the best performance without a multimodal ensemble or fine-tuning. I hope our model CNet is a milestone of deep learning-based nowcasting and weather forecasting model. And yeah, thank you for attention.
Thank you very much. Maybe I can start with the question. I really liked you digging into the predictions that the model makes and how they compare qualitatively with the ground truth and how the loss affects your results. I was wondering, overall predictions, and this is not the unique property of your model, but we've seen this in many of the predictions. The predictions are very smooth, and as a result, look visually quite different from the ground truth in terms of high frequency local properties. And I was wondering whether you had any thoughts about addressing this in maybe future updates to the model to get a more realistic super resolution prediction. If my question is not clear, maybe you want to show one of the slides where you compare the ground truth with the model predictions. Or perhaps related, there's a question by Zuliang Fang, whether the time and spatial losses have a smoothing input on the outputs. So I think both the question on the chat and my own question is related to the smoothness properties of your prediction. And just to be clear, it seems that other predictions are also generally overly smooth. And I was just wondering what your thoughts were on that. in terms of getting not just the average right, which your model clearly does very well, particularly for the transfer learning, but also in thinking about getting more realistic high resolution predictions. Do you have any thoughts or comments on that? Maybe I can repeat the specific question by Zuliang Fang. Do the time and spatial losses have a further smoothing impact on the model prediction output? So basically, if you add your smoothing loss, your spatial loss, and you have a time smooth loss and a spatial smooth loss, right? So when you add these, do your predictions become overall more average, smoother? Do you see that, or do they just make them fit better to the ground truth?
Yes, right. We use spatial smooth loss, and our SHANet predicts smooth prediction. This is our model's limitation.
Okay. I think the question was that you've done an ablation study on the different components of the losses, and that you show that adding these spatial and temporal smoothing losses improves the performance. The question now was, does it qualitatively affect the nature of the predictions in that it makes them more smoothed out as well?
It is true. Our spatial temporal smooth loss is weight, alpha, and beta is used, and each temporal smooth loss weight, alpha, and beta adjust each reason and better performance. But we did not control alpha and beta value because we focused on simple and effective and entertain the patient.
Okay, then there was another short question by Francesco Alessiani. Do you think it is better to have a local or global prediction model?
I can give more information about the question if you prefer. So your assumption is that you have a distribution shift. So you want to be robust, let's say, to this distribution shift. But on the other side, you can also train a local model, to predict what's going to happen locally. In contrast to have a global model that is, that works everywhere. So my question is, did you have any insight from your study to see that a local model would be better than a global model? No? So you augmented data in order to be robust to changes in the location, and so I was wondering if you have seen that maybe a local model would perform better. Let's say. Yeah.
We have not experimented global global data, but we have experimented each region fine-tuning, and our SHANet also benefit fine-tuning its effect.
And additionally, I think local model is better than global because our augmentation policy is based on the legionnaire wind direction, but we can find legionnaire wind direction, but if the domain is more bigger, I mean the global, we can find prevailing wind direction. So it's more difficult in global model.
Thank you very much. And I would like to continue with the next presenter, please. So at the end of the session, we're still having two very interesting contributions by teams from KAIST. The first presentation will be by Jin-Young Park, and we will learn about their approach on units with visual attention blocks. And I'm actually really interested in hearing how this is building on earlier work and adding different approaches.
Then hi everyone, I'm Jin-Young Park from KAIST CI Lab in Korea. Today I'm presenting our work, the rain unit for super resolution, the rain movie prediction under the spatial-temporal shift. And the 4 students involved in this project, me and our Minseok, and also Seungheon and Inyoung. The weather forecast competition is about super resolution rain movie prediction. And this challenge starts with the basic concept that over longer prediction sequence, and particularly in the rapidly changing weather events, the addition of spatial context in the input is necessary for provide the information about moving or precipitation to the model. The next possible question is that how we may successfully use this additional spatial context for the spatial temporal modeling. To answer this question, we propose a super resolution nowcasting model that extracts both intra-frame correlation and the surrounding context, which is the inter-frame correlation. So this is our method. As shown in the figure, the overall structure of the proposed Weyn unit is a hierarchical U-shaped network that intermediate feature are passed through the skip connection between the encoder and the decoder. And the encoder extracts the spatial temporal pattern throughout K stage, and the decoder progressively integrate the spatial temporal information to predict future rain rate. And each encoder and decoder that contains a proposed temporal-wise CPRO block, the TS block in the right side, and the down or upsampling layer. Especially the TS block takes some advantage of the both CNN and transformer, which have a low computational cost compared to the attention mechanism, while capturing long range dependence. To capture the spatial temporal pattern of methodological feature, the TS block is the right of the figure. It contains two submodules, the linear projection and the factorized 3D convolution, F3D conv module. And simply we use a 1x1x1 convolution for linear projection. The proposed F3D conv characterize the richer interframe correlation within the intraframe for the global region rather than only the local neighboring region in the consecutive frames. To this end, we decompose the spatial temporal modeling into two separate steps, the spatial and the temporal modeling. Based on the existing video backbone such as R2 plus 1D convolution as in the middle figure. To this end, we disentangle the 3D convolution into spatial convolution, the S-conv here, and the temporal convolution, TC convolution. Moreover, the spatial convolution is followed by the temporal convolution to enable the interframe temporal modeling. However, due to the locality of the standard spatial convolution, its receptive field is limited, which makes it incapable of investigating the interframe context, which is an excellent clue for the future weather prediction. So another solution can be simply extending the corner size, but this brings a huge amount of computational overhead and the parameters. So to elevate this issue, we inject the temporal-wise delayed convolution, the TSD conv, between the spatial convolution and the temporal convolution, and TSD conv generates the long-range spatial feature and enable the model to focus on the surrounding area required to predict the next frame. So additionally, we introduced a several data pre-processing strategy to handling additional spatial context, including modality selection and data cleansing and the center crop. The input data of challenge comprise 3 different sensing modality, the 7 channels of IR and the 2 channels of VIS and 2 channels of water vapor. And visualization of each channel's types and the target image is shown in the figure. We mainly use the IR channel, which occupies the largest proportion, the 7/11 of the satellite images. So we conduct a toy example by adding a VIS and the water vapor channel to determine which type to use. So we train the base model 3D, which is called the 3D UNet with the belonging setting. And overall, the IR with the VIS produced the best performance. So considering the IOU precision or accuracy like that. So therefore, we use a total 9 channels comprising IR and the VIS for training. And since non-rainy situation occur more often than the rainy situation, the entire data are biased toward the non-rainy situation. So this easily trained the model with the bias for the non-rainy situation. So as we filter the data to reduce the weather bias, to this end, we count the positive pixel in the 30 ground truth future frames. And if the values are less than 100, the sequence are regarded as a non-rainy situation and removed among the total 300,000 sequence. About the 70,000 non-rainy sequence are excluded from the training phase. And also the over longer prediction sequence, and particularly in the rapid changing weather events, the additional spatial context in the input is necessary to provide the information about moving the precipitation to the model. However, if the spatial information cover too wide area than target region, it could rather degrade the performance. To prevent such adverse effect, we crop the center of the input frame and resize it to the 252 square pixel for training. A crop size one time, for example, indicate that we crop the same size with the target region, and moreover, crop size 6 is a kind of non-crop scenario since it cropped the equal size of the input frame. So we crop the center of the input frame to 3 times the size of the target region. So next is the experiment part. Here is a table of quantitative result of our proposed rain unit and compared to the baseline 3D unit. It contains a validation result and weather forecast core test score. And evidently, the rain unit is superior in all metrics compared to the 3D unit. So through the DC, data cleansing, we achieved a slightly shorter training time, making training more efficient and effectively. And also it is clear to show that the center crop is boost the predictive performance. So when both DC and crop are combined with the rain unit, it achieved the best performance on the various metrics like the IOU record or accuracy and test score. And another evaluation study of rain unit architecture, and this result represents the effect of TS block by replacing the encoder and decoder of 3D unit with our proposed method. The best performance is shown in the IOU, record, and F1 score when the TS block are applied to the both encoder and both decoder. So regarding the precision and accuracy, since there is no significant difference from the second best is observed, so we adopt the model in which the TS block are applied to both encoder and decoder. So this is another evaluation study of crop size, and figure 3 shows the IOU performance over lead time according to the crop size. We can define the predictive performance by distinguish into here the short-term prediction and the 6 to 8 hours like the long-term prediction according to the period of the lead time. And in this case, only the small target area with surround context is used for training, like pink line, the crop size 1 here. And the performance within a short period is best among the various crop size, but the performance rapidly degrades over time. So conversely, when looking at the wider area, see the blue, the 6.5 like here. And the short-term prediction performance become lower, but the performance of the long-term prediction is higher compared to the pink line. Then this result indicate that the surrounding information improve the long-term predictive performance. However, there is some trade-off with short-term predictive performance. So based on this observation, we choose the crop size 3 times for our method. And table 4, this one, just summarize the best score, the result. So for the qualitative result, we visualize the output of 3D unit and rain unit in the slide. The output of the 3D unit are similar regardless of time. And however, our method capture the overall change in rain rate over time, and it demonstrating our method's superiority in capturing a temporal relationship. More specifically, the center crop has a crucial role in our model as shown in the result. Without the center crop, the slight output variation occurs over time, but including the center crop reveals a more detailed temporal relationship. And this shows that the removing the unnecessary information helps the model to learn well. So here we report the leaderboard score of our solution in the table. And the baseline 3D unit score is based on what was submitted by the organizer. And we note that our best evaluation results from the held up test set are 0.2871 in the core challenge data set and 0.2357 in the transfer challenge test without any ensemble or refinement techniques. So finally, here is the conclusion. Our contributions are as follows, and we propose a WeatherFusionNet with temporal-wise separable block, the TS block, using a decoupled large 3D convolution to improve the prediction performance. And we also then analyze the modalities are important for precipitation prediction among the IR, the VIs, or the water vapor, the modalities. And we also analyze the importance of surrounding information in detail by investigating with various crop size around the target. So in the context of application, our method is easy to apply wherever data exists. And that is, our does not utilize complex physical formulas or dynamic models and does not require any additional specific location like latitude or like time information. So furthermore, since TS block exploit intraframe and the interframe correlation among video sequence using a surrounding information, and our method will be expandable for general video prediction as well as weather forecasting. So thank you for your attention. So please see our full paper for more visual and detailed and visualization. So thank you for listening.
Thank you very much. So Francesca Lisiani is asking why adding one channel has the worst performance.
Can you explain more about your questions? Because
reduces performance. So I don't know if Francisco, maybe you wish to just speak on the channel. We're a small enough group that we can keep it really formal.
I saw that you presented the performance. You did this selection of the channel, no? Yeah. And the best performance is when you only use 2 out of 3, whereas, so do you have an intuition what's happening? Why this additional channel reduce the performance?
I think adding the water vapor is degrade the performance because water vapor data set has a lot of some noisy data, like there is no information in there. So that might be degrade the performance, I think. So we eliminate the water vapor.
Thank you.
One from me.
Okay, Alexandra.
Okay, so thank you for a nice presentation. And taking into account your test related to different crop sizes, do you think it would make sense to have some kind of, I don't know, hybrid ensemble solutions that uses different data processing crop sizes for different timeline predictions? So different for short term because it behaves differently.
Actually, we didn't try the random crop size, and I think the using the mixing of the crop size can also boosting the performance, I think, because as you can see, the crop size is they training on only the same spatial resolution, but as you know, the various augmentation can boost the performance, and also the small area are good at short-term prediction, and also the large area can help the long-term prediction. And this mixing of crop size can help with the increasing the performance, I think.
Thank you.
Thank you.
I have one question just on the algorithmic side. The attention in the TS blocks, is this something that you're taking from earlier work, or are you modifying this? Is this something that you apply directly based on success in earlier work, or have you modified the way in which you implement this attention?
Okay, actually, we newly build our work. As you know, the before team, the CNet, mentioned about the large kernel convolution, and this is very similar work of our TS block, but conceptually there is a huge difference between us because mainly the large kernel convolution is based on the 2D convolution, and it requires additional consideration for treating the temporal information when extended to space and time data. And as you know, when we're treating the spatial time data, it is really the important thing is capturing the spatial temporal relationship, but just only using the simple extension of large kernel is only consider the spatial and temporal information simultaneously. So since it use more hard the model hard to optimization, and also there also arise a computational cost. And we propose instead decomposing the 3D convolution into the spatial and time axis separately, and which forcing the 3D convolution into this create the spatial and temporal correlation separately. And also that only increase the interframe correlationship. So that's the main difference. And also my answer is that we developed this our own idea.
Okay. Thank you very much. Then we move to the last presentation in this session, where we have another team from KAIST AI, telling us about region conditional orthogonal 3D units and discussing also some training strategies. So the presenter will be Tae-Hyun Kim.
Hi everyone, this is Tae-Hyun Kim. I'm a member of Graduate School of AI in KAIST. Also, I live in South Korea. Yeah, it's deep night. First of all, thank you very much for giving me a chance to compete by providing qualitative data. And also it is an honor to be able to present our methods here. Through this opportunity, all of our team were able to deal with satellite imagery for the first time, and were able to try precipitation prediction. Again, I was surprised that deep learning model-oriented methods could work well. Anyway, now I'm going to present our work, region condition orthogonal 3D unit for this weather forecast competition. And considering the time, we prepared a brief presentation focusing on our novel method part. Yeah, our team members are as follows. All of us are graduate students, except last two, Shin and Seungheon, advised our work. And our team saw that this competition was until October 20th. So we set the schedule according to the plan. It was a pity that the competition period was extended, and we were not able to actively participate in the competition during the later period. Still, during this period, we were finally able to obtain the rank 5th in stage 1 and the rank 1st in the core test leaderboard of stage 2. By the way, in the leaderboard, KAIST AI, KAIST Underbar AI, and KAIST Space AI are the same team. We submitted them under the same account, but we forgot our password, so submitted with a slightly different name variation with space or underbar on team name. Anyway, and next, 2 of the members preparing for this tournament are looking for a new team after finishing graduate school this time, Shin and Yoon. If any of the people listening to this presentation are interested in them, recruiting them, please contact them. Okay, contact me. Yeah, this is a presentation. Let's go on. The contents are as follows. First, introduction, next, methodology, and finally, research, just leaderboard score, and conclusion. So many of presenters and including organizers already present and provide many details about the data sets, so I will skip. So the main goal of this competition is to predict super resolution light movies in various regions of Europe. And so more precisely provide a model predictive length for events until 8 hours in 32 times slots for given 4 time slots of a preceding hour. Data set includes satellite imagery, having 11 observed physics information, positional information, as well as observed rainfall amount. We mainly focus on to develop the performance of stage 1 and stage 2 as follows. And here, in our experience, we include all variables or context as the organizers provided, IR 0162 WV073. And yeah, let's go on. So we did not touch anything about the data set, only focus on to develop kind of prompt-based model modification. So we attempt to keep the model structure, baseline model structure as a unit, and just modify some shortcut or gradient path or adding some additional linear modulator to improve the performance of stage 1 and stage 2. And by the way, where the satellite imagery data demands for the spatial-temporal modeling, the studies for conventional methods are still underexplored for being robust towards such spatial-temporal shifts. Therefore, the main focus of our team is to propose the new method towards the following statement: improve the robustness as well as generalization. So our team serves the challenge of spatial-temporal shifts in a stepwise manner. Step 1, train the backbone network. Here we design the residual 3D unit architecture and apply orthogonal 1x1x1 convolution and inject region condition context. As a training list, we use mix-up and self-distillation strategies. Next, step 2, fine-tune the backbone network for each region of a certain year. Specifically, we facilitate it with film transform. A film is about feature-wise linear modulation. And finally, at last, step 3, apply thresholding for the trained models. So we will explain the details in the later pages respectively. Firstly, this is an overview figure of our architecture. Each blue box corresponds to the residual convolutional unit, and each green block denotes the residual transpose convolutional unit. During the propagation, the region condition context is added to the last output of the encoder, where the shortcut from the encoder unit to the corresponding decoder unit is transformed with orthogonal 3D 1x1x1 convolutional operators, as well as film layer for fine-tuning. The arrow denotes the propagation of a multi-channel feature map. Yeah. Here, for the architecture side, we modify the 3D unit baseline model 3D unit architecture by adding the residual shortcut for both encoder and decoder blocks. Next, to inject region information into feature maps during the propagation, we propose a new region condition network, RCN, to generate region condition context. Here, the given data set is comprised of satellite context for 7 different regions in Europe for stage 2. So during the training, during the inference or propagation, anyway, so the region information is transformed into an one-hot vector, one-hot encoded, having the ranks as 7. We extract the region condition context, including scale gamma vector and bias beta vector as an output of RCN with a categorical input one-hot vector, and then formulate the feature map as the right equations. X equal the gamma multiplied X plus beta. As a next, during the shortcut pass, we applied the orthogonal convergent kernel. Some attenders are not familiar with this kernel, but briefly, orthogonal convergent kernel is a class of the advanced normalization techniques to preserve the magnitude of propagation signal, as well as to reduce the redundant features in the filter response. Because there is the difference of resolution size between input and output, it is needed to capture more fine-grained features from the written representations. Inspired by the orthogonal concept, we alleviate such issue by adding one by one conversion into the path from the encoder block to the corresponding decoder block, and making those convolutions soft orthogonal with the orthogonality regression. In this work, we apply spectral restricted isometric properties plus SRIP plus regression proposed by previous team to one by one conversion of filters as follows. More precisely, more easily, this regression is added to the die species loss we used, and the model is updated with the backpropagated gradient of such loss. Simultaneously, we applied a backup training strategies, mix of data augmentation, and self-distillation. Since satellite image dataset rarely contain lengthy data compared to the abundant non-lengthy data, the model is easily biased towards the majority class, non-lengthy. I mean, to mitigate the bias on the majority class and encourage elaborated classification on the minority class, we applied mix-up. Similarly, as a next step, since the ground truth observation is sparse and noisy, its training is unstable as well as overconfident. To release this concern, inspired by the previous work, analysis of self-distillation, we applied the self-distillation loss, which is well-known technique for smoothing the loss landscape to read a flattened optimum. Then, after training the backbone, we obtain pre-trained backbone. The pre-trained model is fine-tuned with each regional data for each year. For fine-tuning, we use the film transfer called FIT, underlevered in next year's ICLAIR, ICLR, also top ML conference, anyway, which fixes the pre-trained backbone and fine-tunes only film adapter layers. We initialize the new learnable parameters for linear modulation, scale gamma, and bias beta, and modify the written representations of shortcut paths from encoder to decoder during the fine-tuning. The detailed process for film layer is shown in the right side of figure as follows: orange area. So feature map X is transformed into X tiered with gamma and beta from the film transfer, not the region conditioned context. Then after fine-tune, we obtained 14 personalized models from fine-tuning for each region and for each year. So for example, 2019's Boxy 0005 model, and next Boxy 0014 model. Anyway, so for each, after getting the personalized models as a last step, we generate the optimal prediction output by controlling the threshold for each region across a year by thresholding. Yeah, generally the model decides positive rain if the corresponding probability is over 0.5. However, because all regions have different precipitation distribution, this characteristics leads to a suboptimal due to different scales of certainty on each region, even after the film transfer. So as below figure shows, it is needed to set a threshold for each level to get binary predictions. In this competition, we also attempt to find the optimal threshold that maximizes the F1 score for each fine-tuned model based on the validation set. So this is the result and conclusion. Through the combination of our proposed method, we can achieve more generalized model for stage 2 core test score leaderboard, as well as core Helder score leaderboard. Yeah, that's true. To conclude, our contributions can be summarized as follows: effective and applicable and reproducible. First, we utilize two concepts: region condition network RCN and orthogonality Lagrangian on 1x1x1 conversion layers. So the backbone structures are not significantly changed. So with additional training strategies, our solution outperforms a baseline up to 90.54% with less than 1% additional parameters. In my thinking, our method can be applicable to other structure architectures such as transformer-based methods. So it has many potential in my thinking. It has many potentials. And next, our approaches can be adapted to any other deep neural networks and reproducible from our source code at this link. This is the end of my presentation. I'm also in open to work, and thank you for listening. Any contact for collaborative study will be fine. Thank you.
Thank you very much for your presentation. We already have a question by Francisco Aliciani asking whether you could explain the advantages of using orthogonal convolution.
Yeah, it is very confusing and complicated concept. So maybe all you guys know. In the neural network processing propagation, the input is transformed to output with the matrix, Weyn matrices. So if the Weyn matrix is orthogonal, then the magnitude of input and the difference of magnitude between input and output is near zero. Because of the characteristics of orthogonal matrix. So to obtain these characteristics, we applied orthogonal Lagrangian. But if we apply if we generate strictly orthogonal convolution, then it might later hinder the generalization. But if we apply soft orthogonality through such as Lagrangian form, then we can have more advantages from during the propagation.
Okay, thank you very much. I have a short question. You say you optimize your threshold so that it optimizes the F1 score. That, of course, in a very unbalanced setting is a bit different from, say, optimizing a single class IOU. Have you seen big changes in the performance of your model as a function of this threshold? Would it perhaps make sense to set the threshold so that the Weyn class IOU is maximized?
Yeah, very good question. We tried both of the way to maximize the IOU score, or the second to maximize the F1 score, but the trends are very similar. So our first approach is to use F1 score, so we keep the previous approach.
Okay. Any other questions? If not, then I would like to thank Seungheon again, and also all the other presenters in this session. And we would now come to the awards and credits for this year's competition. So I should say that it was difficult as always to choose the prizes. We had a large scientific committee that helped us assess all the submissions in terms of their scientific quality and decide on the final distribution of prizes. Everyone presenting today has received a full conference registration for the virtual NeurIPS this year. And you are also all invited to contribute to a joint NeurIPS proceedings paper. NeurIPS competition track proceedings paper. And in addition, we are lucky that IRI, the Institute of Advanced Research in Artificial Intelligence in Vienna, can sponsor some cash value prizes for some of the best teams. So in addition to the highlights that we've heard in this session that came out of research on this competition, it's my great pleasure to announce the award of the third prize ex aequo to the team calling itself Team Name by Yury Belousov, Sergey and Brian Pulfer from the University of Geneva in Switzerland and NeurIPS in the United States. You've heard Brian present their work on the competition today, combining different visual transformers in an ensemble. So Brian, I don't know if you want to say a few words.
Maybe I will just take advantage of the occasion to thank the organizer of the challenge and all the people that provided the data and the infrastructure to submit predictions and so on. And yeah, just thank the organizer for this competition on my side.
And thanks also for all other participants. It was a really nice challenge. It was a pleasure to compete with you, and thank you, everyone.
Thank you very much. So the Institute will be in touch regarding the 1,000 euro cash value prize towards the end of the year or early next year. And thank you again for your very interesting contribution.
Thank you.
Thank you.
And I should say that we are not presenting the results today regarding, we've also done a significance analysis of the rank differences across the teams. So this wasn't just an arbitrary decision. Indeed, the two teams on the third rank in the core held out leaderboard, they're indeed statistically not distinguishable in terms of the score. Which brings me to the second team winning the third prize ex aequo, ranked slightly higher on the leaderboard, but as I said, statistically significantly so. This is the team SI Analytics from Korea, South Korea. You've heard Minseok talk today, and his other team members include Doyi Kim, who you've also heard talk later, Seungheon Shin, Eunbin Kim, Siwon An, and Yiji Choi. And I apologize for the probably very incorrect pronunciation of the names, but I wanted to give credit to everyone on the team. It is also a 1,000 euro cash prize, and I don't know, Minseok, so maybe you want to say a few words on behalf of your team.
First of all, thank you for opening this great contest, and it was an honor to participate in this challenge. And we think it was quite a really great opportunity to looking and dealing with some climate data sets. Yeah, that's it. Thank you.
Okay, thank you very much. So that then brings us to the second prize by Team meteoai from Microsoft in the US and Nanjing University of Information Science and Technology in China. Team including Yang Li, Haiyu Dong, who was presenting, Zuliang Fang, Jonathan Weyn, and Pete Luferenko, showing us their work on space-time transformers under different context sizes. Haiyu Dong, do you maybe wish to say a few words?
Really appreciate the opportunity to attend this competition. And this is a very interesting topic to explore. The data, the model, the strategy, many things to explore. And we found many interesting findings. And also we found more opportunity to explore deeper, like the model, the data strategy, and the data training strategy versus the model solution. There's more to explore. Really appreciate the opportunity for this competition. Thanks very much. And also, I really learned a lot from a couple of discussions and presentations today. Really learned a lot. And thanks for the competition. Thanks for the workshop. Thanks.
Thank you very much. That brings us to the first prize, which was awarded to the team of FIT-CTU and MeteoPress from MeteoPress and the Czech Technical University in Prague. Jirí, Pihrt, Rudolf, Raevskiy, Petr, Šimánek, and Matej, Choma. You've heard Petr, Šimánek talk today, showing how incorporating physical models and units gave them the leading edge in the core challenge in this competition. Petr, do you perhaps wish to say a few words?
I will only repeat the previous speakers. I want to thank you and the whole committee and reviewers, as well as the other competitors, because we have seen very diverse solutions of the same problem. So it was very, very interesting to us. And I would like to say that we are open to collaboration on this topic in the future. So if anyone is interested, we are as well. Thank you.
Thank you very much. And there is one more special prize that I need to announce. It goes to the Team SI Analytics again. This is the special Transfer Learning Challenge prize that the scientific committee has decided to award to this particular team because of the interesting and successful performance of the team in the Transfer Learning Challenge. You've heard Doyi present on their model and how it approaches this trick. And this will also be dotated with a 4,000 euro cash value award. Doyi, do you perhaps wish to say a word or two?
Yeah, thank you for your special prize, and thank you for organizing this challenge. I can learn the weather data set, and also I can learn the transfer learning and many other things. Thanks.
Thank you very much.
May
at the end, I should perhaps say that, oh, you want to say? Okay, go ahead.
Yeah, I just wanted to add one thing to this transfer learning challenge, because Team SI Analytics, they also got the first prize on the transfer learning leaderboard. And this is actually very, I say, nice coincidence. But the main idea of this prize was actually to award the most interesting approaches to the transfer learning. So just for all of you who are here, it was not decided simply by leaderboard position, but actually by the content of the paper submitted. And I just wanted to stress it.
Thank you, Alexandra. That's a key point. This was debated at length in the scientific committee, and perhaps that's a good lead into my closing comment on the prizes, that there's still an opportunity for a best paper award. This will be based on the presentations in today's session, and also your contributions to the joint manuscript in the proceedings. So this is still another prize that is up for grabs, and if anyone wants to go fish for it. But we hope that these prizes are not your main motivation, but just sort of an occasion or a sign of appreciation from the community. Because at the end of the day, at least we as organizers are mostly driven by our curiosity in the science here. And I wish to take this opportunity to thank everyone who has made this competition possible, and everyone who has submitted and put their enthusiasm into the competition. In this line, I would like to actually again mention that this was organized by the Institute of Advanced Research in Artificial Intelligence with strong support by IAMET, our key partner on the data and meteorological side, and contributions by ESA and the SUT. I would also like to mention the scientific committee that included both meteorologists like Javier Calvé as well as people from the computational side, like our very own Seb Hochreiter, Bertrand Lesson from ESA, and Alexandra Gorutza from the SUT. But certainly also Piotr Mirovsky, who has made pioneering contributions to the modeling of weather using deep learning, and Michael Kopp from the IRI. Contributions on the baseline models and the data were also critical to get this going on a data set of this size, to ensure that the data actually contains structure that can be exploited in deep modeling. And there I would like to thank our partners at IMET and ESA and SUT, and both internally, so that's Michael Kopp at IRI, Federico Serva at ESA, Lawrence Liso at IMET, and Alexandra at the SUT, as well as Pilar Ripodas at IMET, Anna Kaiser von Lerber at Opera, who provided the Opera data, and Pedro Heruso, who took first steps in getting all these data together. And this is not a small task, actually. Many of you mentioned the infrastructure to support all of this and to make this competition possible. We have a fairly large team on the back end on this that keeps things running, and I'd like to highlight Moritz Neun and Christian Eichenberger, our senior contributors on the engineering side, as well as Miriam Masquez, who was responsible for all the design and a lot of the website things, and Alina Mihai, who's kept it all together. So with that, I think we're coming to the last session here, where we would like to very much invite all of you to perhaps share your thoughts and ideas for the coming year, considering that the time that people have had on the large stage 2 dataset was just a month. We're currently contemplating whether to just leave the dataset in place for next year, but move the challenge from a binary rain event yes no prediction to a more challenging quantitative prediction, because the data are already in your hands, if you like. But the challenge, of course, is much harder, with one aspect of the difficulty remaining, that these are extremely zero inflated data. And what we've seen from past modeling efforts in the field, this really is an issue. People that do well on the standard mean squared error have extremely smoothed out solutions that are not realistic model predictions in any sense, meteorologically speaking. And of course, it will be interesting to think about what error terms to use, what actual metrics to quantify the performance of predictions, particularly in the zero inflated context. And I would like to open the floor to a general discussion to everyone regarding your experiences from this year looking forward to next year, and whether there are any aspects or concerns that you think we should particularly consider. Also, I would like this opportunity to invite anyone who is interested in contributing to the development of this framework, as in how we actually evaluate predictions in this quantitative scenario in the next year, to get involved with us. We're not a closed group. We're open to all scientists who are interested in shaping this competition. One thing one could also consider are, of course, loss terms that, or error terms that punish predictions that look very unrealistic, say they're over smooth or something like that, or they lack temporal correlation, temporal coherence. Yeah. So I think I can stop sharing here because there's not a lot to go. But I would like to open the floor to general comments or discussion in this context. I think we're not that many people that we need to rank things, but on the chat you can either just speak out or raise your hand.
Okay, so maybe I will just try to simplify this question before we go into the actually new types of metrics. And I would like to ask you, actually, what do you think about having two-class IOU problem?
Perhaps to clarify, the current metric was a one-class IOU, so in intersect over union just for the rain events, because otherwise, if we have two classes, then the second class with the no rain dominates if we just take the non-weighted mean. And if we weight the mean, the question again is how you weight it. I mean, do we weight it the same for all the regions? Do we weight it, you know, with a true positive weight for each region and so on? So that was the reason why this year's leaderboard was a one-class IOU. I know that there are quite a number of papers that use something like a CSI index, so the CSI value to again look at the performance of getting the prediction right for a certain threshold. And we have seen in Weather Forecast 2021 that even the rank on the leaderboard changes quite considerably as we change the threshold. So this is an issue that is reflected in a lot of the recent literature, that the way you select your threshold for a CSI, and also similarly, of course, for the IOU, affects how the models perform. If you train a model to perform well at a particular threshold, it will not necessarily do well on another threshold. So whether we do that with one class or two classes, perhaps from the meteorological side, there are thresholds that are meaningful from the weather side. So one could go for a multi-class scenario where the thresholds are even externally from application relevant considerations. I mean, you will see that we moved from the simplest 0.0 threshold to a 0.2 threshold for the rain rate for the second stage. And that was actually informed by our meteorological partners, who said that this is a threshold below which a rain prediction is actually not that application relevant, that meaningful. So perhaps some of the groups on here who have been working and modeling weather before have a comment on this and their experiences and their recommendations or preferences.
Maybe if I can, we tried to model just precipitation, just predicting radar, and we unfortunately don't have the answer. We spent quite a long time trying to devise the metrics, the loss function, and also the metrics, and we don't know what is the good solution right now. And I think it would be good to make it a regression task, because it will show more relevant results. Like you can really check how the rain, if some structures are kept, maybe easier with the regression task than with the multi-class or two-class. Multi-class is probably okay. So maybe one question is, why do we need to predict 8 hours? I think it's super difficult, and if we would change it to, let's say, 4 hours or something more, something easier, maybe we could focus more on the short-term prediction, which is doable, because like last 2 hours could be virtually impossible. And if sorry.
No, please. Sorry, I have the lag. So.
And if we focus too much on the last, let's say, 2 hours, it could hamper our efforts to improve the first 6 hours, maybe.
That's a very good point. So yeah, I hope we can come to some form of a regression loss, where the challenge will be how to handle the zero inflating. And perhaps we can again run 2 stages, but this time each stage could have more time, so that there's plenty of time for the first and plenty of time for the second stage. now that the data are all ready. And then maybe in the first stage, we can explore different losses and different prediction horizons to then settle on something that's meaningful for the second stage. I agree that the 8 hours are hard. We picked 8 hours because the leading models at the moment claim they do pretty well for 8 hours or 12 hours. Of course, these are massive models trained on similarly large amounts of data as we present here. But the qualitative properties of the predictions actually still show problems there as well. So I don't think the problem is solved at all. And if you think it might be more interesting to start with a shorter term prediction, maybe 4 hours or so, if there's a reasonable consensus in the community, why not? We can actually have separate leaderboards, one for the first 2 hours, the first 4, the 8, and see whether there's extra insights to be gained by splitting this up.
Yeah, makes sense. Thank you.
Okay, Julian Fang has a question whether we plan to improve the quality of the radar data. Well, maybe you can expand a bit what concerns you have about the radar data. We have so far released one of the 2 variables that we've collected from the radar. Maybe our partners at IEMET, if they're still on the call, can comment on this. There is something we might be able to improve on the satellite data, but I'm not sure I can promise, because these data are have a 2% noise added to them. That was a condition for us to be able to release them, because otherwise every participant would have had to enter a written agreement with EUMETSAT, and that's quite a barrier of entrance. So we thought having a 2% noise is maybe a good trade-off versus not having to do paperwork. But maybe by the time the final stage 2 next year comes out, we will have sorted out some better legal compromise with them. I don't know. But Zuliang Fang, can you comment a bit regarding your thoughts about the radar data? What concerns you have there?
Sorry, I'm Pilar. So I don't get what is the problem with the radar data.
Yeah, I was just asking Zuliang Fang, who asked the question, to clarify what they meant with the quality of the radar data. So, Zuliang, can you perhaps comment?
Hi, if I can add on this, I think with radar data, it's also available a sort of quality control flag that could be provided. So indeed, some data are by nature problematic due to some sensor malfunction or whatever. So maybe a sort of quality flag could be maybe useful. I don't know if Pilar knows more about it.
Oh, I can comment a little bit. Maybe Zuliang did not put the question very correctly. So that's not really the quality issue of the radar. It means no matter the different angle of the reflectivity, that's the surface reflectivity or the composite from different angle, and then the quality control to make the composite. And then there's a process to convert the radar reflectivity to precipitation rate. And also there may be difference between the radar observation with the station gauge observation, or even with the user perception. So that's a very generic question, not specific to the data of this challenge. So just an open question. Maybe that's already an existing, a very hot research area in this on the radar and satellite and even station gauge data. That's my understanding.
So
okay, I think I
Pilar,
didn't get everything, but yeah, I mean, we have provided just the intensity of precipitation, and this has been calculated using the Marshall-Palmer relationship. We all know that this is not a perfect relationship, but it depends on the kind of precipitation you have, it is convective or not. But I mean, this is what Opera is providing. And I mean, it's very difficult to put together all the data from the different radars, from different met services, different characteristics, and so on. So we have to rely on what the project has done to put all together and to get the best of it, because it's very difficult to get some homogeneous data for such a big area. And I don't know if I'm answering the question. And yeah, of course, we are just providing the precipitation intensity. There are other parameters like the maximum reflectivity, or that could be provided. This provides more information, but still there are other information that is missing. The radar data is taken through the volumes of precipitation. So we are not providing this. So for sure, there are a lot of more information that could be provided, but we don't have this, you know. And it would be very difficult to deal with this information also, because, as I said, because of the different radars and different characteristics and so on.
Yes, thanks. That's also similar feeling for us.
Yeah, I mean, I understand that, but please correct me, Pila, if I remember this wrongly. I understand that we also have the radar reflectivities and I think maybe even a second parameter, but we considered that providing the rain rates directly would make it considerably easier for the models. But if anyone thinks that would be more helpful to have raw data, we can probably get some raw data.
We have those data, we just don't, basically.
But we just have, it's the intensity that we have provided, and then we have the maximum reflectivity in the vertical. So it's not just the reflectivity, because this is a 3D volume.
Yes.
And what we have is the maximum reflectivity in the vertical and the 1 hour accumulation. And these are the composites that we have. We can always provide this information. I guess the reflectivity could be more useful because the accumulation, somehow you already have the information. You have to add the instantaneous values. But the reflectivity is providing some extra information, can be related to the kind of precipitation you have. But,
the question then would be, what is the output variable that we want to
well, the output would always still be the
intensity precipitation.
They all come, all come from Opera. They're all Opera products.
You're right. That doesn't necessarily help.
Okay. And I would like to do another comment about the leading time of the forecast. I also think that 8 hours is too much. Too difficult, and I think that 4 or 6 hours, not more, would be fine, because starting, I don't know, 5, 6 hours, the numerical weather prediction models are doing well, I could say. So it's important. What is important are the first hours, really.
I mean, one thing I should perhaps also mention is that the data are getting quite large. So the whole competition data repo is already about 400 gig, and distributing this in a scalable way is also a bit tricky. I hate to say we had to turn off the S3 for distribution for some destinations because they kept getting downloaded again and again. That's not sustainable. We have to pay for that. So that's also a reason why we're limiting the type of data that we're sharing to those which we hope are the most helpful. So if there are any ideas regarding the ground radar, we're of course always interested. Are there any other thoughts or comments, questions, ideas?
I would be interested. It would be interested to hear also your comments about the context area size, because we had at least 2 presentations that actually analyzed the provided context size, and it seems it's not really optimal. So I don't know, should we make it smaller? Like I recall the 3 times, I think, was picked by one of the case team. Also, I think the meteoai suggested that the size of the context 3 times of the size of the 3 times of the region of interest is a good choice. So I don't know, it's better to provide smaller context, and then of course we have less data. Also for sharing, which would be easier for download.
I'm sorry.
Or maybe it's better to provide bigger one and then actually let this decision to the participants.
Sorry, I didn't mean to interrupt. I think one of the earlier presentations had a 2-fold reduction in resolution, and that was optimal for them. I guess if we're going for shorter prediction horizons, like 4 or 6 hours, the bigger context becomes probably less relevant. One of the reasons we also provided the large context was to let people, if they want to, learn the relationship between the raw sensor bands and any rain also on the big context, just to provide more data. So since the data is out already, I'm not sure we need to cut it. I mean, we could for someone to download it newly to make it faster to download. But using less data is always something people can do. But indeed, it seems that for the current 8 hours, even the whole context was too much. I mean, the context was determined partly also by the thought of how fast does a fast cloud possibly move. And in most situations, maybe the clouds aren't that fast. So yes, it may have been too large from a meteorological point of view. So we could go to half, say, if that's helpful.
Oh, actually, I think we can keep it, because one finding or thinking of this is that even though for now we can use the 3 times as the optimal context, and in the Magnet 2 paper of Google, they also mentioned that 4 times. Their spatial context 2048 to forecast 512. And they didn't explore a larger context than 4 times. But with this data, we explore them. As I mentioned earlier, even we input a large context, which already includes the existing optimal context, the model cannot learn it well. So that provides us a request. Our current model, the model we are using for now, is not capable enough. If we feed it more, it cannot digest what it can digest. It cannot learn what it can learn within a small context. So the model capability is not enough. That's one of the findings I got. So if we keep this large context, then we can further explore better modeling. If we can just input it with such a large context, but the model can still perform very well at the short and also long lead time, and even longer lead time, longer than 12 hours. So that's a demanding for a better model. That's my rough idea.
Perfectly fine. Thank you. Thank you, Haiyu.
Actually, I have a question to our participants about static data. I'm not sure if there was any team that used it.
But not a lot.
And for those...
As I mentioned quickly in my presentation, we tried it in the experiment, but we didn't. We found that it cannot provide model gain, and so later experiments we didn't use it. And also we checked the presentation in the special session of last year. The author of DGMR, the DeepMind paper, they also mentioned that the static data did not help because the storm, the convective or the precipitation, the short, especially in short term, is not related to the static data. But this is also one thing that we need to explore more.
Yeah.
And other comments? Thank you very much.
Yes, I actually have a comment. I should say that the competition rules entirely permit people to use any other data sources externally to these data if they think it makes their prediction better, except of course cheating as in getting the rain from some other source. But for instance, if someone wanted to get ground temperature up to the time for which the prediction needs to be made from some other source, that they could, yeah. I'm not saying that this allows for a direct comparison on the leaderboards, but it certainly gives additional insights. We had this on the traffic forecast competitions where we provided additional information to people that were predicting traffic, like about points of interest on the maps. Or for instance, if you know that somewhere you have a shopping center, you might think there would be more traffic there at certain times. But it turns out that for most tasks and for most situations, actually this data wasn't helpful at all. So also trying to use an external data source and finding it does not help can be interesting in a way. I just wanted to say that the data that we provide is the basis for everyone, but people wanted to use any other data, they're entirely free to do so as long as they declare it and as long as that data is open to everyone as well. So it should be public data or data that can at least be shared. So if someone wants to explore complementary nature of additional input data, that they're more than welcome.
Yes, that's also one of the ideas that we'd like to explore, to add more atmosphere variable, especially to the decoder. We can input the NWP forecast as a constraint.
Okay.
Okay, so I think there's one more comment on the chat that I just wouldn't like to leave without comment as well. So if the BitTorrent could be an option for data, so I think this is related to the huge volume of data to download and the fact that we actually had to block this our Amazon S3 bucket. And the answer for this is a little bit complicated because this is related to the licensing issues. So not all the data we actually can put outside our servers. This year, for example, we couldn't put outside the Opera data because of the license that we had. So this data set was only available to be downloaded from the weather forecast website. The satellite data we could provide from outside.
Yeah, and they're the biggest chunk. So maybe exploring BitTorrent is a good idea.
It's called academic BitTorrent. So sounds
academic
actually
BitTorrent. Okay.
Not very bad. Like it's an academic torrent actually.
Academic torrent. All right.
Yeah. So thank you for this comment. We will check that.
Anything else? I don't want to cut anything off prematurely. On the other hand, I appreciate that you've just had 3.5 hours of session with no break. I really appreciate your contribution and your interest. If there are no more comments, I thank you all again, and we much look forward to an extended and more advanced hack at this next year, where we will try to actually track the quantitative predictions in some advanced regression approach. And if there are any questions or something, you can always contact us on the weatherforecast@IRI address. We're always open and keen for input. Thank you very much, and goodbye.